All right, you can give your attendances now. So hopefully all of you can see the screen. So yesterday we left at legendary transformation. So just to summarize, what we have learned is that suppose you initially had a function uh, that was a function of x, y, and z. And then you computed this is df was x dx plus y dy plus z dz, and so these things were basically the derivative of, so this was del f del x. And if we wanted to construct a function that was where we replace small x by capital X, but we do this by defining g equals xyz, where g is given by, so let me write it down. So g x y z would be given by f x y z minus x times small x. Okay, and from that we got the relation that uh, we will have in terms of this new function del g del x equals minus x, del g del y equals capital Y again, and del g del z equals to capital Z again. So this is the summary of yesterday's last part of the class. Now, if you compare this thing with our Lagrangian formalism, so we have initially a Lagrangian, which is a function of q dot q and t. Okay, so just compare these things with x, y, and z. So q dot is my x, q is your y, and small t is your z. So then you can write basically, so del L del q dot, which is basically your p, and that will play the role of capital X. Then del L del q, that will play the role of uh, capital Y. Okay. And del L del t, that will play the role of capital Z. Now I can define a function. So if I define something like this, so let us define a function that is L q dot q t minus, so remember this is x times x, so x is basically my p, so p times q. Following the convention, I will call these functions to be the minus of h, so that would be a function of capital X. So first of all, this should be a function of capital X. So capital X is basically p, then q and t. So if I define this legendary transformation, then I construct this function, which I will call my Hamiltonian, to be this L minus p times q. Okay. Now, so basically g, the role of g will be played by minus h. Okay, so let me write it down. So the role of g is played by minus h. Okay, so from the first equation, so del L del q dot equals p,
So will it be,
equals x.
excuse me, sir?
Yes.
So will it be minus like PQ, because if we are defining P by Q dot, like dou L by dou Q dot. So in multiplication, it should be like Q dot.
What is q dot? I do not understand. What do you mean q dot?
Sir?
This one?
No, sir. So in the where we are defining this thing, minus H on the right
Oh,
extreme.
right. Yes, yes. So that should be q dot. Yeah. All right. This is a mistake. All right. So the role of g will be played by minus h, and okay. So from this equation, del g del capital X equals minus x. So I would write. So this equation will take the form here. So it should be minus del h del p equals minus x, and x is q dot, so minus of q dot, yeah, which basically translates to q dot equals del h del p. Then you get the second equation. So del g del y equals y. So y is your small q. So here the second equation will be minus del h del q equals y. Y is del L del Q. So y is del L del Q. Okay. Now from Lagrange equation, you know this del L del Q is basically d dt of del L del Q dot. But del L del Q dot is basically P, so this is dp dt, or in other words, this is my P dot. Okay, so this is my second equation, is P dot equals minus del H del Q. And third equation again uh, should be del G del T, so that is minus del H del T should be equals to Z, and Z is del L del T, should be equals del L del T. Okay. So these three equations, in summary, uh, are called the Hamilton's equations of motion. So here I have actually considered the one-dimensional version of Hamilton's equation, when you have only one generalized coordinate q, and corresponding to which you have one generalized momentum that I called p. But in general, if you have many different generalized coordinate and the corresponding generalized momentum, you will have this n set of equations. So suppose h is a function of rather say pk, qk, t, and where k runs from 1 to say n, you have n generalized coordinates. Then by the same token, you will have the Hamilton's equation to be qk dot equals del h del pk, and then uh, pk dot equals minus del h del qk, and the last one is obvious, the same. This is del h del t equals minus del L del t. Okay, so these are your Hamilton's equations of motion. And more than often you will encounter a situation when your Lagrangian will not explicitly depend on time. So the last equation in most of the times becomes redundant. This so this becomes redundant uh, if L doesn't explicitly depend on time. Okay. So this is the thing, and that's why you often, when I talk about the Hamilton's equations, usually we mean the first two sets of equations. So so the first thing you notice that in the Euler-Lagrange formalism, if you considering Lagrange's equations, then there were n number of second order differential equations. So the Lagrange's equation is a second order differential equation, but here you have 2n number of first order differential equations. So 2n number of first order differential equation. Okay. So in a sense, it is the same. Either you might like to solve n number of second order differential equation with proper boundary conditions, or sometimes you might find it easier to solve 2n number of first order differential equations. But that is not the advantage of the Hamilton's equations. Hamilton's equation has other advantages, which I will come in the later part. But first, I want to point out a couple of subtle things. So when in this formalism of introducing Hamiltonian, I never used L to be written as T minus V. I never talked about kinetic energy and potential energy. Okay, so what I used is that so L is a function of Q dot Q and T. I do not know what that is. Like by I do not know what that is, I mean that that is a function that has been constructed artificially by some artificial guesses, by some symmetry arguments or so. If it becomes T minus V, it is an happy accident. But my point is, given a function which I call Lagrangian, I can construct a function which I will call Hamiltonian, where this q dot variable can be replaced by what I call the generalized momentum P. Okay, and it does not necessarily need to have a straightforward interpretation as physical momentum. It's just a quantity which I call my generalized momentum. So this whole Lagrangian and Hamiltonian approach, the way I am treating it, is independent of whether you can define a kinetic energy or potential energy or not. So the power of this formalism is that even you do not understand what is meant by kinetic energy and potential energy of a system, you can still write down a Lagrangian or a Hamiltonian formalism for that system. Okay, so now before I proceed further, I want to give an example that given Lagrangian, how to construct a Hamiltonian. Perhaps many of you already know that, but I want to stress on a couple of points here. So let us go back to the central force problem in two-dimensional polar coordinates. Let's say I write down my Lagrangian, which is a function of the generalized coordinate derivatives r and theta, sorry, and which is given by half m r dot square r square theta dot square and minus Vr. So this is the Lagrangian of a central potential in, say, 2 dimensions. Okay. So your job is, what is Hamiltonian? So what is the Hamiltonian? So first thing you should do is that you should try to find out the generalized coordinates and the generalized momenta and replace the coordinate derivatives in terms of the generalized coordinate and generalized momenta. So your first job, so step one should always be that, so your step one should always be that you should express your the coordinate derivatives qk dots as a function of the other p's. So let's say qk as a function of pi. So for that, what you need to do, you need to find out the generalized momentum. So the first generalized momentum, let's say pr, is given by del L del r dot. That comes out to be m r dot. Okay, and p theta would be del L del theta dot, and that is given by m r square theta dot. Okay, so in general you have n such equation, right? Because if you have n number of generalized coordinates, you have n such equations. And in this particular scenario, these equations are disentangled, like r dot only depends on pr and theta dot only depends on p theta. But in general, things might not be so simple, and you have to do some tricks to solve the coordinate derivatives in terms of the momentum. But you must do that. So basically, from these two equations, you will obtain r dot equals pr over m, and theta dot equals p theta over mr square. Now you define your Lagrangian, now you define your Hamiltonian as your L minus, basically PR r dot minus p theta theta dot. Okay, so that is the definition of your Hamiltonian. Sorry, this is my minus of Hamiltonian. Okay, so next, so this L is again a function of r dot theta dot r and theta. Now in this expression you basically replace r dot and theta dot by these things. So r dot should be replaced by this and theta dot should be replaced by this here and here also. So in the functional form also you should replace theta dot by that. And then at the end you should only have expression for Hamiltonian which depends on, there is no r dot and theta dot flying over. So if you do everything correctly, that should be 1 by 2m pr square plus p theta square by r square plus pr. Okay. Now notice at the end there is no r dot and theta dot anywhere. So in the final expression for the Hamiltonian, if there is coordinate derivatives, okay, then you get 0. Okay. So remember, when you find the Hamiltonian, you have to express it in terms of the momentum and the coordinates only, and no coordinate derivatives would be there. Okay. So now that you have found the Hamiltonian, incidentally this can be interpreted as t plus v. So because this is a conservative system, so this can be interpreted as t plus v. So now if you check your Hamilton's equation, so first of all r dot would be given by del h del pr, which is pr by m, and in the next part you get pr dot, that is given by minus del h del r, that is equals p theta square by mr square minus dv dr. Okay. So you notice that the first equation gives you the definition of linear momentum, and the second equation gives you the force law in the radial direction. Okay. So you convince yourself of that. So here you get PR equals m times r dot, which is the definition of linear momentum, and that gives you the force law in the radial direction. Again, for the theta direction, you similarly get theta dot equals del h del theta is equals p theta over mr square, and p theta dot equals minus del h del theta, that is equals to 0. Okay. So now so now again, and this equation gives you the definition of angular momentum. So this gives you the definition of angular momentum, and this is a restatement of the Noether's theorem that the angular momentum is conserved. So this means that angular momentum is conserved. Okay. So in this way, Hamilton's equation does not give you anything new. to because these are the same conclusions that you would have obtained from your Lagrange's equation. Okay. Next, I will discuss what are the advantages of Hamilton's approach. But before that, let me pause here and let me see if there are questions up until this point. Any questions?
Hello, sir.
Yes.
Sir, if you do this calculation and there is no relation between the coordinate, the derivative of coordinate and the momentum. So there, how can we find the relation?
No, if you do this, there will always be a relation between your momentum and your coordinate derivatives, because the equation is pk equals del L del qk dot, right? So, and this thing depends on q dots, and this is the quantity that you introduce. So now you can solve q dot in terms of this pk. Just practice a few different problems. And
Sir, if in the question, if say only r dot is given, then by doing the differentiation, we get only a constant. Then that point how can we?
I do not understand. What do you mean by r dot is given? You have one coordinate then. So
Sir,
if
sir, suppose Lagrangian is half m r dot plus r square theta dot square minus b or something like this, and by doing the differentiation del L by del Q dot, we are finding a constant like half m. Then there is no relation between r dot and p r. At that point, how can we find?
again, I still do not follow basically. So I mean, this del L del Q dot in general is a function of Q dot. I mean, usually for a physical system, it is a function of Q dot.
Okay, but okay, sir. Okay, sir.
If you come across some examples, you can tell me later. So if you come across a problem where you have problems in defining this generalized
Yes.
momentum.
Yeah, yes, sir. Sir, I was going through the net question, and there is no relation between peer and that's why I was asking this question. Sorry, right now I haven't that question right now, but something like by doing the calculation, there was no relation between the coordinate differentiation and the momentum. So I was a little bit confused about this.
Well, I didn't know about any such examples. If you come across later, you can let me know. Okay.
Okay, sir. Thank you, sir.
All right. Any other questions? Okay. So then let me continue. So the particular advantage of this Hamiltonian approach is quite apparent when you are dealing with cyclic coordinates. Okay. Okay. Now, the general the general method I am trying to discuss is that suppose you have a Hamiltonian uh, which depends on, say, two generalized momentum p1 p2 and q1 q2, but let's say q2 is cyclic. Okay. So I have q2 is cyclic. So since q2 is cyclic, then basically from Hamilton's equation, you will have P2 equals constant. Okay. And if P2 is my constant, then you can replace it by a constant that is C, that is determined from your initial condition. If you know the value of P2 at some time, and it stays there. So you just plug it back in here. And then H becomes a function of P1, Q1, and some constant C. But this C is a constant. It's just like you can treat it just like a parameter. So this apparently two-dimensional problem, by virtue of Q2 being cyclic, becomes a one-dimensional problem now, because the non-trivial dependence of H is on P1 and Q1. So this effectively becomes a 1D problem. Okay. So in general, suppose you have a Hamiltonian that depends on say P1 dot 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 up to Pk dot 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 up to Pn, and then you have Q1 up to, let's say, Qk minus 1, and then Qk plus 1, then up to Qn. Okay. So what I mean here, that let's say Qk is cyclic. So here you notice that there is no Qk, so that means Qk is cyclic. Okay. So initially it was a n-dimensional problem. There was n first-order equation, but since Qk is cyclic, you can replace this Pk by a constant, that is C, and now what you have, it's basically a n minus one dimensional problem. For example, let us go back to this problem here. So this one. Okay. Here I have found p theta dot equals 0. That means p theta dot, so p theta is a constant. So let me call p theta to be a constant C. Okay. Now if you replace this in this expression for Hamiltonian, okay, so this Hamiltonian will now look like, so H equals 1 by 2m PR square plus C by R square plus VR. Okay, maybe this is C square, whatever. It's a constant. So I noticed that this Hamiltonian only depends on R and PR. So this is something that depends essentially on R and PR. So I have reduced my problem to an effectively one-dimensional problem. Okay, so although my problem was, to start with, my problem was a two-dimensional one, I can use the information for cyclic coordinates, and I can reduce the number of effective dimensions, and I can simplify my scenario here. And the only non-trivial equation I get comes here. Okay, so this is the momentum, and this is the only non-trivial equation that I need to solve, and I replace p theta square by c square here, and this is just a radial equation in R. Okay, and the solution becomes simple. Okay, so this kind of simplification you can do in the Hamiltonian approach, but notice that you could not do that in the Lagrangian approach. So you might say that why I cannot do this thing in the Lagrangian approach. Suppose take the mirror image of this one in the Lagrangian approach. So in the Lagrangian approach, what will happen? So L would be a function of, let's say, Q1 dot, then up to Qk dot, and blah 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 up to Qn dot, and then Q1 the same way, Qk minus 1, then Qk plus 1, and then up to Qn. Okay, which is nice. Still Qk is cyclic, so you can see here still Qk is cyclic, and you still have that del L del Qk dot equals constant. Del L del Qk dot equals constant. So just by having del L del Qk dot equals constant, it does not imply that Qk dot will be a constant. So you cannot replace Qk dot with anything in general. For example, here I had m r square theta dot equals constant. What did I have? So p theta equals constant. That is p theta is your am r square theta dot. This is equals to constant, but by no means does it imply that my theta dot is a constant. Okay, so that's why I cannot in the Lagrangian formalism. And the problem is still two-dimensional because I cannot replace theta dot with anything. Okay, I have to treat theta dot as it is. But in the Hamiltonian approach, I can, if there is a cyclic coordinate, the solution for the momentum is trivial, and I can use that freedom to replace the generalized momentum corresponding to the cyclic coordinate as a constant and effectively reduce my number of dimensions there. Okay. And this particular aspect, this particular trick that I described would be your bread and butter for something called the Hamilton-Jacobi theory. Okay? So this is one of the things that you would be using in Hamilton-Jacobi theory, that you will find the cyclic coordinates by one mean or other, and then you simplify the problem in the Hamiltonian approach. Okay. Now there is another interesting thing about this Hamiltonian approach, which is the concept of phase space and how to visualize the evolution of a system. Okay, so let me now introduce something called the phase space. Okay. So it kind of is an easy way to visualize the evolution of a system. Okay. Again, to effectively visualize, I have to again move to the one-dimensional problem when Hamiltonian only depends on say P and Q. Okay, so what you know is that if you know the momentum and the coordinates of the particle or of the system at all time, then you know the system at all point of time. Okay. So suppose this is my q axis and this is my p axis. Okay. So this p and q might have some general features. So how does it behave in this coordinate system, in this two-dimensional coordinate system? So if you have one generalized coordinate, then that means your phase space is two-dimensional. So in a similar way, if you have two generalized coordinates, then your phase space is four-dimensional, which of course I cannot draw. And in case you have n generalized coordinates, then you have your phase space is 2n-dimensional. And perhaps you had been introduced to these concepts in your statistical mechanics courses, but nevertheless, let us revisit those concepts a bit here. Okay. So suppose at time t0, the particle, I consistently talk about particle, but when I talk about particle, I mean any system that can be described by such a generalized coordinate and the momentum. So suppose that system had a momentum p0 and position and coordinate q0. So p0 q0 represents a point here. So this can be this is given by, let me write it as q0 p0. So this is the system at t equals 0. So what you have here is basically p0, let's say, is equivalent to value of p at t equals t0, and q0 again the value of q at time t0. So somehow you can locate the particle at t equals 0. The particle or the system is here. So this is at t equals t0, the system is here. And the whole point of Hamilton's equation is that the Hamilton's equation basically describes the evolution, the time evolution of this point. So because remember this P and Q will evolve according to P dot equals minus del H del Q, and Q dot equals minus del H del P. So given a H, so given a H, so this H basically, no, it's not minus, governs the time evolution of this P and Q. So that means starting with T, Q0 and P0, so the evolution of this point would be governed by the Hamiltonian. So this is the time evolution. So so at time t, particle reaches here, and it takes this path. And so from here to here, how will the system evolve from this point at t equals 0 and this point at t equals t is governed by the Hamiltonian. So basically, this is the time evolution of the system that is governed by H. Okay, so H governs this time evolution uniquely. Okay, and this takes a unique path. Okay, so you can basically think about how you construct this kind of path. So this is a very important insight that you should get used to when you later do things. So that basically tells you after time, so this is basically dp dt is equals minus del h del q. Now this del h del q is a function of p and q, right? So you have been given a Hamiltonian, and if you take the derivative of the Hamiltonian with respect to q, you get a function of p and q. So let me call it say f1 pq. Okay, and at t equals t0, that particle was at p0 q0, right? So at t equals t0, the coordinate was q0 p0. So at that instant, dp dt would be given by f1 p0 q0, right? So this is my thing. I just substitute p0 q0 in that thing. So now at a time t equals t0 plus delta t, what will happen? Delta t is very small. Then my dp, so my delta p would be f1 p0 q0 times delta t, right? So it tells me how will be the change in my momentum. So my p0, sorry, so p at t0 plus delta t would be given by p0 plus this delta p, which is again given by f1 p0 q0 times delta t. All right. In a similar manner, you can you could have written that dq dt is del h del p, which is another function of p and q. So let me call it f2 pq, and then q at t0 plus delta t by the same spirit would be given by q0 plus f2 p0 q0 delta t. So given the position of the by position I mean the phase space coordinates. So this kind of pair of coordinates are called the phase space coordinates of the system. So if the system was here at t equals t0, the Hamiltonian tells you uniquely. So if you know the Hamiltonian tells you uniquely that at time t0 plus delta t, where the system will land upon. So the system will land upon a new pair of coordinates p and q, which is given by this. Okay, so now, so it tells you that from here it will move to, let's say, here, because this is my, right, so this is my evolution in delta t. Okay, now from here you can again play the same game and the particle will go to here, and then let's say here. So that's how I draw this evolutionary curve for this particle, or this, for this system. So that's what I mean by the Hamiltonian governs the evolution of the system uniquely. So it builds on step by step at small infinitesimal steps. It builds upon that the evolution of the system. Okay, and the evolution of the system is entirely governed by the Hamiltonian. Since this evolution is unique, uh, you notice that no two evolutionary path can ever cross each other. Okay, so suppose let me draw again a coordinate system. Maybe the arrow is better. We put an arrow here. Okay. So suppose one system starts from here and the evolution takes it to here, okay, at time t, okay, and another system starts from here that is governed by the same Hamiltonian but with a different initial condition. Okay, so that means it can never go, say, you can say it, if it takes this route, let's say at t equals t. So this can never happen. So no two evolutionary path can ever cross each other, because if it does, then it means that at the crossing point there are two different routes that the system could have taken, and since my Hamiltonian is uniquely defined, I cannot have two independent evolutionary paths, okay, from this point. So once I landed on this point, so from this point on, which path the system will take on phase space, it is uniquely defined by the Hamiltonian already. So these kind of things cannot happen. So you learn a few things here. So how to visualize your evolution of a system. So basically, that you can display the evolution of systems that is governed by the same Hamiltonian in the same graph as different space-time points. So suppose one starts from here and it at time t it goes to there. So another suppose starts from here at time t it goes here. Let me undo this thing. Yeah, it goes here. Then there is another evolutionary path. Let's say it goes here, okay, something like that. So this means that, so this yellow, blue, and red lines represent basically the evolution of the same system. So these three things basically together. So this is evolution of the same system. By same system, I mean that they are governed by the same Hamiltonian. So all the system are governed by the same Hamiltonian from different initial conditions. Okay. So they look different because they started off from a different phase space point at t equals 0. So initially, so this different initial conditions means the different starting points. So the same system, they had different starting points. And the Hamiltonian basically evolves them according to their evolution. I mean, if you have trouble understanding this thing. Suppose you can consider a particle falling under uniform gravity. Now, what is the situation of the particle at t equals 0? Suppose I will talk about these things in detail in the next class probably. Suppose particle of mass m falling under uniform gravity. Okay. So you know that so this statement of the problem doesn't talk about the initial condition that the particle of mass m was there. So suppose if we are considering only vertical motion, so if you initially throw the particle upwards, okay, in this direction, so pr equals, let's say, so this is my positive z direction. So at this time, so pz equals, let's say, some it has a positive value, so 2 gram meter per second. Okay, and it starts at z equals 0. So at t equals 0, it starts at z equals 0 and pz equals 2. So basically, the q equals 0 and pz equals 2. So the particle basically starts from somewhere about here. So this is the initial condition. But suppose you, instead of throwing it upwards at the initially, you just let it fall from a height h. Okay. Suppose you, this is basically the same problem. The Hamiltonian is the same. It's just uniform gravity. So you are standing on the rooftop or a tower. So this has a height h. Okay. And you are basically making the particle fall from here. So initially the momentum is 0 because you are starting from rest. Initially the momentum is 0, and z is equals to h. So suppose somewhere over here, so this is the point, is basically h and 0. So it starts from here and this side. Okay. Rather, if you so like that, you are now, suppose basically throwing the particle from this rooftop at a momentum say 3 upward. So then the particle will have this movement like this, right? So you see, depending on the initial condition, the description of these three motions are different, right? So the initial condition governs that, and in the phase space, it looks like, so so it's from h and momentum 3. So maybe it starts somewhere from here. Okay, so this is what phase space does. So from the phase space, the evolution, you can say what was the initial condition. You start at the initial condition, and if you know the initial condition, you apply your Hamilton's equation of motion, and you get the unique trajectory. You get the unique trajectory of the system in the phase space. So it's basically the, write down the unique trajectory that is dictated by the Hamiltonian. Okay. So given a Hamiltonian, the phase space evolution is unique. Of course, I have done it for one dimension, because for only one dimension you can draw these coordinates. But for n dimension, when your phase space system is of 2n dimensional, all these things goes inside your head, because you cannot draw a 2n dimensional coordinate system. But you can somehow, you can basically in your mind, you are visualizing, okay, it's at the evolution of a point in 2n dimensional phase space over time. And that's it. And that is one of the advantages of the Hamiltonian approach, and it gives you a handle to visualize how the system evolves with time. Okay, so I will stop here for today, and let me know if you have questions.
Sir,
Yes.
sir, I found that question. That question was L equal to, sir?
Yes, I'm listening to you.
Sir, half q dot sine square q.
half q dot sine square q.
Yes, sir.
Well,
Here is Lagrangian, and we have to convert it into Hamiltonian. But by doing first differentiation with respect to q dot, we are finding just a constant, not a constant in terms of q. Then how to approach after this, sir?
this is a bit strange. I do not have an answer of out of my mind right now. I mean, I'm actually surprised to see this kind of a Lagrangian. Okay, I'll think about it.
Okay, sir.
Okay.
But in the answer key it was given that we can't find the Hamiltonian. That's why I was asking, sir.
Yeah, I mean, for this scheme, probably the Hamiltonian scheme cannot be defined, but I have to check on that.
Okay, sir.
Okay. All right. Anything else?
Sir, just show the upper slide before phase space, just before phase space.
This one?
Yes, sir, this one.
All right. No other questions then? Okay, then if there are no further questions, then I will end the session here, and I'll see you again tomorrow.